Great. So hi, everyone. Welcome to today's AFMS seminar. It's my pleasure to introduce our speaker for today, Associate Professor Jason Hearst from the Norwegian University of Science and Technology, NTNU. So Jason received his PhD in 2015 from the University of Toronto in Canada. His main research focuses on the experimental investigation of turbulence, primarily by the generation of bespoke turbulent flows using active grids, and he'll be talking about some of this research today. So please go ahead and take it away, Jason.
Thank you, Kat. Thank you for everyone who's logged on. So I'm excited to share some of this work we've been doing on the effect of turbulence on turbulence, which is a deliberately catchy name. You'll see what I mean by this as we go through. So as Kat said, I'm from the Norwegian University of Science and Technology, and that acronym NTNU doesn't make sense in English, but it makes sense in Norwegian. And just before we get started, I just want to say that most of what I'm going to show you today has been funded by, the Research Council of Norway, and some of it is funded by the European Research Council. On the same vein, as we know, when we do modern science, almost nothing is an individual effort. So what I'm going to show you today is not just my work, but is a work that's a collaboration between many people. And everyone who's contributed to today's talk is here on this slide. So thank you to everyone who has made this work possible. Oh, we've jumped around by mistake. So I'm up here in Norway. I'd like to give a little bit of context of what's going on. Most of you are down here. And a question we frequently get. So we're in Trondheim in Norway, which is not Oslo, and we are just below the Arctic Circle. So it's not winter or dark or light here all the time. We do get all the seasons though. So we have nice flowers in the summer, we get fall, and there's snow, and northern lights are a thing that happen in Trondheim. NTNU has 42,000 students, so we're actually the largest university in Norway. And we're primarily a technical university. For those of you who have studied grid turbulence or wall-bounded flows, Per Åge Krogstad, who is now retired, was the fluid mechanics person from here. So for those of you that do grid turbulence or roughness, you've likely read some of his work at some points. And just some last background on the city. We have these colorful wooden houses that Scandinavia is known for. Norway has beautiful fjords with waterfalls. And this last picture is actually a picture I took with my phone from my house. So northern lights are a real thing. So more to science. We do primarily experimental fluid mechanics in the group that I work in, which is a thermal fluids group. And we have many facilities, but two of our primary workhorses are our wind tunnel, which is 11 meters long, 2.7 meters wide, and 1.8 meters tall. It was recently refurbished to give us optical access so that we can do PIV. And our water channel, which is new, commissioned in 2019. It has similar dimensions. It's 1.8 meters across, and it can have about 8.8 meters of water depth, and is also 11 meters long. And one thing that makes both of these facilities unique is that we have active grids. We actually have a lot of active grids. I'm going to talk a little bit about what these are as we go through the slides. But in essence, these are devices we put at the inlet of the test sections. And as the flow goes through, turbulence perhaps naturally is produced as it tries to get through this blockage. And the elegance of the active grid is that we can adjust the way it is moving. So this is what you're looking at is not flow induced. This is driven by stepper motors. And by adjusting the way that the wings move, we can exert some control of the turbulence intensity and the length scales that are produced downstream. Just a quick note on these three particular grids I'm showing you. The wind tunnel active grid on the left is the second largest one in the world. The largest one is at Oldenburg in Germany. Theirs is 3 meters by 3 meters. The water channel one is, to my knowledge, the largest one in water in the world. And the planar jet channel flow one is less special in itself, but as you can see in this little video, each wing is individually controlled. So we can create fun patterns like this spiral that you're seeing here. Just for scale, this is the wind tunnel active grid being presented by Hilda, one of our researchers. So it's the size of a person. Before I get into depth of flow physics, just a quick word on what's actually happening behind these grids. So if you consider just this first case here, which I'm calling ref, this is when we don't actuate the active grid. So essentially it acts like a passive grid. The flow moves through it, some turbulence is produced as it goes past the bars, and it produces a relatively low level of turbulence in our facilities. In some cases, for instance, in the water channel, that generally water flows have higher background turbulence, the turbulence intensity doesn't change when the grid is present and not actuated. Then what we can do is actuate some of the wings. So for instance, here we're actuating half of the wings, only the horizontal ones. So you can see that along a single axis, so for instance, if I draw a line along here, all those wings are moving the same way, and that's because one stepper motor is controlling them. But each axis is controlled by a separate stepper motor. So we're sending different commands to each line of the grid here, basically. Generally, we give them a top hat distribution. So for instance, the distribution of velocities would look something like this, where we're going from plus some frequency to minus some frequency. And we use a top hat distribution because we've seen in some previous studies that this produces roughly homogeneous turbulence downstream. Now what we can do is actuate more wings. So here we're actuating all of our bars, and this will increase the turbulence intensity that's produced downstream. And then, for instance, we can slow them down, and this produces the highest turbulence, which is perhaps counterintuitive to some people, but this has been demonstrated in several studies that basically as we move the wings slower, the turbulence intensity increases. So what you're looking at here is we use randomly distributed along a fixed frequency, frequencies that we put onto the whole grid, and we're deliberately making this uniform across the grid. There are some other groups that also use active grids that do things that are perhaps more creative, where they're flapping them in different ways, or they create a transfer function where they measure at one point at different angles and then try to reproduce certain flows. And this stuff is all very interesting. It's not the way we tend to actuate our grids because we're trying to produce HIT, so homogeneous isotropic turbulence, or something that's very close to that. But if you are interested in these other ways of actuating the grid, feel free to message me and I will point you at literature from other groups that does this. Now, just a quick sanity check, or mostly for info, is that this is grid turbulence. So it decays as you move away from the grids. So here I've listed turbulence intensities that I'm calling U prime naught over U naught. And that's, we take some reference location just so that we can compare the different sequences. But as you can see, the turbulence intensity does change downstream, roughly follows a power law like one might classically expect. But the important thing is that in terms of the way we label them, that these are just for reference, and that you can see the cases never cross each other here. The highest turbulence intensity case is always the highest turbulence intensity case, just for example. And the fact that it evolves is something that we will talk about as we go on in this talk. So just a little bit more historical context. The first active grid of this style was made by Makita in the early 90s in Japan. And as such, this type of active grid is often called a Makita style active grid. We later saw them appear at Cornell, and then through the 2000s, a few more popped up. And in the last kind of 10, 12 years, we've seen many more active grids pop up around the world. Last time I updated this was during COVID, and I think some things have changed. So if you are watching this talk and you have an active grid and you're not on my list, please let me know. I'd love to update my map so that it is current. But as you can see, these devices are becoming more and more common around the world. So that was a little background on the active grids themselves, but what I really want to talk about is what we use them for. So we generally run our grids to create a version of homogeneous isotropic turbulence, where the flows are homogeneous. They do evolve in space, and our worst approximation of the isotropy part is that we get to maybe 20% of isotropy in the worst case. Sometimes we are 100% isotropy. And when I'm talking about 20% isotropy, I'm referring to the ratio of span-wise velocity fluctuations and the stream-wise velocity fluctuations. So I'm saying that this number can be something like this, where ideally it should be 1. But So we produce these flows with these active grids. And what we want to see is what happens when we produce this turbulence and how does it affect other flows. So for instance, these three are very canonical flows. We study them at length in idealized scenarios in the lab and in DNS, where we have for instance, as close to laminar free stream as we can produce. And then we look at a planar jet, we look at a planar wake, we look at wall-bounded flows. And these studies are very important because it basically is a simplified version of the total Navier-Stokes equations. And it lets us understand what are the driving mechanisms. But they do differ a little bit from what we see when we come out of the lab, in that there are very few flows that have perfectly laminar free streams around them. So we've kind of had a program here. What we're trying to look at is, can we bridge this gap between our idealized flows and flows that happen outside of the lab by changing the incoming conditions, that is by adjusting the turbulence above them. And what does that do to them? What does that do to the flows? Are they the same? Do they care? Do these effects disappear downstream? And that's what I hope to share with you today. And then the last one is a new thing we've been looking at, which is how does turbulence affect air-water gas transfer, which is important to the total climate system. And we'll talk about that a bit later. It's a little bit different than the first three, but also very interesting. At least I think so. So before we get in and jump off the deep end, I just want to talk quickly about spectrograms, because some people are very familiar with them and some people have not seen these so much, and they're going to pop up on a few slides. So this is a way of visualizing the spectra in a wall-bounded flow. So just what you're looking at here is, this is the wall normal direction, normalized by inner units or outer units, where delta is the boundary layer thickness, plus shows us normalization by viscous units. On the side, we have wavelength, again, normalized by inner units or outer units. In many other studies, we'll use lambda for wavelength, which is a more intuitive variable perhaps, but lambda is a reserve variable for us when we do free stream turbulence, and that we use it for the Taylor microscale. So I'm using zeta here for length scale. So now if we draw a line here and we look at the spectron at this one spot, this is what it looks like. This is pre-multiplied form. And this is a very characteristic shape for the near wall region, where you have this near wall spectral peak. And then for instance, you can draw a line here and you pull out another spectra. And this is characteristic of the outer peak that you see in wall-bounded flows. And the point is that this spectrogram is just stacking all of these spectra together into a contour plot. So what are these spectrograms supposed to look like? This is a paper from Nick Hutchins and Ivan Rusik from Australia. This illustration from this paper, I don't know what other people frequently bring up, but this illustration is always stuck in my head. I think it's a very great figure that tells you a lot of what's going on in a boundary layer. And I just want to point out what we're actually looking at here. So here's your mean velocity profiles, where we see a log region, wake, and the start of the buffer region of viscous sublayer. Here we have the variance profiles, where we have this characteristic near wall peak and the variance. And these are the spectrograms. Now, Reynolds number is increasing like this in these plots. So what you see here is that there is this outer spectral peak, which starts to evolve as you increase the Reynolds number of the flow. So basically, we want to know, does this happen when we add free stream turbulence? And if it's different, how and why is it different? So here is the experimental setup. This particular experiment was done at the University of Southampton while I was working as a postdoc there with Bharat Ganapathy-Subramani. So what we do is we have a boundary layer plate, and we have our active grid upstream. We run our active grid through a few different sequences to create different free stream turbulence. And then we look to see how this interacts with the boundary layer and what the boundary layer looks like. Just broadly, some things that happen, so you can try to picture what happens when we add free stream turbulence, is that just focusing on the right. As we increase the free stream turbulence intensity, we see that the turbulence intensity at all positions is increased, both near the wall and away from the wall. And then when we look at the mean velocity, generally increasing the free stream turbulence intensity makes the boundary layer fuller. So by that, I mean we're putting more momentum closer to the wall. So these are in linear space, but we often look at boundary layers in semi-log space. So focusing on the right side first, what you see is that as we're increasing free stream turbulence, so really that's increasing the turbulence out here. We have elevated turbulences in the outer layers, but that comes all the way into the wall. And even the near wall peak is heightened by increasing the turbulence out here. And then if we look at the mean velocity profile, we see that we're recovering a log region that roughly follows our expectations for the log layer. We do see a buffer region incoming into the viscous sublayer, but where there's the biggest difference is in the free stream, where the empty symbols are a reference case, so a normal turbulent boundary layer, whereas the colored symbols are our cases where we've added free stream turbulence. And you can see that the wake, so that's this structure here, is suppressed. And that manifests as something that looks flatter in the linear plots, which was the more which was this phenomenon here. So that manifests like this on these plots. So this is the elegance of the active grid. We have one experimental setup, and we can change the initial conditions through many, many settings by just adjusting the free stream velocity or the grid settings. So these are 17 cases that we've done. We roughly divide them into cases where we produce the same free stream turbulence intensity. And then we use the active grid to manipulate the integral scale. So in some cases, because unlike what I'd like and many people would like to believe, we can't just dial in whatever we want. The flow has limits and the facility has limits. In some cases, we're able to have some sort of change on the integral scale. This one, for instance, is 50%, and this one is about 65%. But in some cases, we can't affect as much change. But what we're going to look at is basically these cases where we have roughly the same turbulence intensity, can change the integral scale somewhat. And what happens? Does the boundary layer care? Does it look like those original spectrograms and profiles from Hutchins and Marusek? Does it look different? So that's our objective here. So just to start off, these are all of the mean velocity and the variance profiles from all those cases. They're grouped into cases of the same turbulence intensity. So remember that although the turbulence intensity is the same for all of those groupings, we change the active grid setting, which changes the spectra and the integral scale. So it's changing the large scale organization. But the takeaway from this slide is that although we're doing that, it appears that the boundary layer profile for these turbulence intensities cares mostly about the turbulence intensity and not so much about how you organize the actual spectrum in the free stream, at least in terms of these first statistics. I would say, because this is a question we get a lot, that this is different than some of the older studies. And two of the main reasons that we think this is one, our turbulence intensities are much higher than some of the older studies. And two, we are much further away from our grid, which is a benefit of the active grid. So there's no inhomogeneity in the flow where we're doing these measurements. And I'm not saying integral scale isn't important, because as we go through the talk, you'll see integral scale does matter quite a bit for some flows. But so let's look at our spectrograms and our profiles again. So here, what we have is these are increasing turbulence intensity from here to here to here. And you're looking at spectrograms, mean velocity profiles, and the velocity variance profiles again. And I want to compare them to these, the canonical results from Hutchins and Marusek. So here again, their Reynolds number is increasing in this way, like this. And our Reynolds number, if you look at it, also increases in this way. As we're increasing the turbulence intensity, we're increasing the Reynolds number. And then if we look at their outer peak, it evolves as you increase Reynolds number. And for us, it also evolves as we increase the Reynolds number, except the difference is in our flow, we're increasing the Reynolds number by changing the turbulence intensity. So one thing that is a major takeaway here is that although we've destroyed our wake, we have spectrograms that look quite similar, and the measurements on the right are from a boundary layer facility that is about 20 meters long, whereas the ones on the left are from a wind tunnel that's 4 meters long. So we're able to simulate some things from the higher Reynolds number facilities in a much smaller facility, by using free stream turbulence to basically try to mature the boundary layer earlier than it should. So let's look into this a bit more. In each of these cases here, we have increasing turbulence intensity as you go down, which is increasing RA theta as well. And then in each pair, we have different large-scale organizations. So by that, I mean the active grid is producing the same turbulence intensity, but actually moving in different ways. So the spectra in the free stream look slightly different, which you can kind of see in the edge of all of these plots. But what I want to focus on actually is this region near the wall, and that this near wall peak looks quite similar between all these cases. And in fact, if we pull out the spectra along y plus equals 15, we see that the near wall peak is the same for all of them. So no matter what we did to the large scale organization, that near wall peak did not change. And all of the changes in the turbulence intensity all manifested out here in the outer regions near the, so still near the wall, but that information didn't get to the near wall peak, it stayed at the larger length scales. And an interesting byproduct of this result is that if you were able to take a measurement at y plus 15, and this, because this curve always looks the same, even in these turbulent flows, you could infer what U tau is from this single measurement. Which is interesting. Now, of course, how you know where y plus 15 is a priori is another question, but there's some universality in what this peak looks like and where it is. So that was a bunch of statistics about spectra, mean velocity, and the variance profiles. But what about the instantaneous structure? So what do these things actually look like when you take a snapshot of them? So this is a snapshot of our reference case. So that is a laminar, roughly laminar, low turbulence free stream. And this next discussion I'm going to frame in the context of the interface with the free stream, which for the canonical case is a turbulent, non-turbulent interface. And then uniform momentum zones that are populated below that interface. This is a quite common feature of turbulent boundary layers. It's been documented since the 90s, and more recently there's been a bit of revival in this sort of analysis. But generally, instantaneous pictures of a turbulent boundary layer show that it is layered in these structures that have roughly uniform momentum, and that the smooth mean velocity profile is a consequence of averaging many of these images together. Instantaneously, we don't see a smooth profile at all. So we want to know, what does this picture look like when we've added free stream turbulence above the boundary layer? So this again is done in the tunnel at Southampton with our artificial wall. We're using our active grid to generate turbulence. And this time we're doing PIV with 3 cameras giving us this view, although we will mostly focus on a central column. These are 3 instantaneous images of different cases. So this is our reference case, so low turbulence free stream. And then we have 2 cases beneath it with 8% free stream turbulence and 13% free stream turbulence. And our question is, what do the instantaneous structures of this look like? So first, we find that we can identify a top edge of the uniform momentum zone area for all the cases. And this is actually important in identifying uniform momentum zones, because if you can't find this edge, then basically the free stream masks out the UMZs. The way we typically find UMZs is, like I said, we mask out the flow above this wall-bounded region. We look at a histogram of it, find some peaks. And these peaks represent modal velocity, so that is the velocity inside the uniform momentum zone. And then we draw thresholds between the peaks. And we see that this results in the layered structure for the canonical case. So does this work for the cases with free stream turbulence? And we do find that we can identify these structures, but perhaps more interesting than can we find them is, are they the same or are they different? And these instantaneous pictures actually illustrate some of the differences already. One is that you see that for the increased turbulence cases, that the spot of the interface is lower than it is for the reference case. So the UMZs are contained closer to the wall. And another one is that there are fewer UMZs in those 2 instantaneous pictures compared to the reference one. So this is just what that instantaneously looks like, but let's actually look at some statistics of that to back up what I'm saying. So this is a probability density function of the instantaneous position of the top edge of the highest UMZ. I'm using this terminology because what we call that interface for the turbulence cases is a little bit more debatable, but this would be the turbulent, non-turbulent interface for the reference case. It roughly has a Gaussian shape to it. Now, what you see for our two turbulent cases is that one, the location of the top edge of the top UMZ it spreads out over a wider area, so it can be located in a much broader range of positions relative to the wall. And two, as we increase the free stream turbulence, the most likely position for it to occur moves closer to the wall. So what that's telling us is indeed the UMZs are contained to look closer and closer to the wall as we're increasing the free stream turbulence. Now, what about how often they occur or how many there are? So as we increase the free stream turbulence, there are fewer and fewer UMZs that we can detect. And do we want to take a question in the middle?
Yeah, can I ask a very quick question?
Oh, it's up to you, Jason. Because we can.
Go ahead.
Okay.
Is this a zero pressure gradient boundary layer?
Yes, it is.
Thanks.
Yeah. Thank you for the clarification question. Yes, these are zero pressure gradient boundary layers. So what we see is we have fewer and fewer UMZs, and that they're located closer and closer to the wall. Some small features that some of your eyes may be drawn to is one, the peak for our highest turbulence is at 1, and that is true, that is the peak, but these cases actually represent more total cases than that peak does in itself. It's a PDF, right? And two is that you see that along the axis here, the two turbulent cases do not go to 0. So what that's telling you is that we have cases where we see no UMZs at all. And that number increases as we increase the free stream turbulence intensity. So I will give you a summary of all of this wall-bounded stuff when we finish the wall-bounded section, just so you don't need to remember everything as we go along. But we frequently, while we were doing this analysis, got questions from reviewers, and we had it ourselves. That is that boundary layers actually evolve in space. And everything I've shown you so far is at one position that is downstream, where we trust that the boundary layer has evolved sufficiently and the turbulence has evolved sufficiently. But this is one spot that we're looking at. And we also know that grid turbulence evolves in space. So the natural question is, what happens to these flows in space instead of just at this one plane where we've documented extensively so far? So here we come to the NTNU facility, where we have our Waddle channel that's 11 meters long. We have our active grid upstream, and we use one component LDA to measure velocity profiles at several positions. As I show you the LDA, you'll see that the data is slightly scattered and more discretized than it was for the hot wire measurements in the PIV. And one of the main reasons is that we do have physical limitations when we do experiments. And that is that to converge these statistics, we were sampling for 10 minutes per point. So basically the profiles I show you is what we could reasonably capture in a day of measurement. You'll see there's still, we still get a lot of information out of it, but the thing I'm pointing at is just that there isn't as much data here as there is in the PIV. So these are the active grid cases we use. These are actually the images I showed you earlier, where we're adjusting the grid in different ways to create 4 different base cases. Again, these reference turbulence intensities are for here. And we just use them as an identifier to tell you which case is the most turbulent and which case is the least turbulent. It doesn't mean that the turbulence intensity is this number the whole way downstream. Down here, we're showing you the Taylor microscale Reynolds number, which is generally the Reynolds number that characterizes how turbulent something is. And you see that our Reynolds numbers are going from roughly 30 to 500 at our various measurement positions. And this is high for these type of experiments. And then let me pull those back off. These are the RE tau we have produced, where we're starting just below 2,000 and our highest one is around 5,000. So again, these are high numbers for a facility of this size, but they're not high Reynolds numbers compared to what you can get, for instance, at Chiclope or the super pipe, where we're getting closer to order 100,000. So what did we actually do? We measured at multiple downstream positions. This first plot, you can see things that look quite like that first one I showed you. So this is increasing turbulence intensity. It also results in this near wall peak being bigger. and that we have higher turbulence intensity in the outer regions. And just for your reference, the black line is our reference case. So that's our lowest free stream turbulence case we can produce. And then you can see here that they go green, red, blue as we increase turbulence intensity. So now what I'm going to do is I'm going to populate all the data onto here. So we measure also 55 mesh lengths downstream and 95 mesh lengths downstream. And I'm going to break this down for you. You don't need to try to discern something from these plots. The point is just to show you all the data in one spot, and so you can kind of see some trends going on. And one of the main things I'll show you for the mean velocity is that we are getting a log region and a viscous sublayer, and that the biggest changes are out here in the wake region. So let's break this down into a little more detail. What you're looking at here is the first measurement station, the various different free stream turbulence cases. And now I will populate the next measurement position and the next measurement position. And now we...
Oh, sorry about that.
No problem. So now we see some changes between the cases. First off, the peaks were quite dispersed here, but as we go to our furthest downstream position, the near wall variance peak has become quite similar for all the cases. So that's telling us that we're getting something that's a bit universal if we allow it to evolve far enough. And two, if we compare the wake region to here and here, we see that we're starting to get some wake recovery between the cases. So that is starting to look like the canonical profile that should do something like that. So let's compare these in a different way. Here, what we're looking at is we have increasing free stream turbulence intensity in this direction. And what I'm going to populate onto these curves is the evolution of that particular case. So this is as we go one position downstream, as we go two positions downstream. And first, let's just look at the canonical case over here for the variance profile. What we see is that we have a slight growth in the peak as we go downstream, which is what one would expect until it eventually gets to a spot where it will stop growing, we think. And then what we see is the emergence and a strong development of the wake region in the flow. So this is what you would expect for a canonical turbulent boundary layer to happen, and that is what happens. Now let's jump over to the most turbulent case. And what we see is actually something quite interesting. That is this peak, instead of growing, that's not what it's doing. It's actually shrinking. So in some context, and we're going to look at this in the spectra as well, this boundary layer would seemingly be becoming less mature because you expect this peak to grow and then stay somewhere. Instead, this one is shrinking down. We do see in the outer regions, though, that the wake is growing in both these turbulent cases. And this is just a zoom in of the wake to show that it is growing. So let's look at this in terms of the spectra. So we've established that the inner peak is relatively robust to external or free stream turbulence. What you're looking at here is this is evolution in streamwise position, and this is increasing turbulence intensity. So for our first three cases of turbulence intensity, what we see is what we expect, that is that this outer peak grows as we move downstream. So the boundary layer becomes more evolved, it's starting to develop this outer spectral peak. But very interestingly, for the highest turbulence intensity case, this peak goes the other way. So we have a strong external peak initially, and that this peak disappears as we go downstream. And the reason for this is that that peak was actually imposed by the free stream turbulence, and that as the free stream turbulence dies out, so does that peak, because the free stream turbulence isn't as present. And this might seem intuitive now that you see the answer, but what we knew before was only this row, right? So all we knew was that the free stream turbulence had evolved the boundary layer to some more mature state. But now what we know is that, yes, it does do that, but then the boundary layer effectively devolves as that turbulence dies out. So the important takeaway there is that the turbulence does not permanently mature the boundary layer. Instead, it has a direct impact where it is present. And as it dies out, that boundary layer reverts back to its premature self, not to some older state, as if it had already been matured. So to close out the wall-bounded section, our question was, do internal flows behave the same way, or are there some differences between internal and external flows? So looking at this, we're doing a channel flow this time. So we have our blower at the inlet, we put an active grid. Our facility is 109 heights long, its aspect ratio 12, so it behaves a lot like a channel should. We did measurements at 100H and at 87H, but like the truth is, we got a better camera when we did the 87H ones, and those measurements look better, and upon comparing 87 and 100 in the first and second order statistics, they were the same. So I'm primarily showing you stuff from 87H, but we have high confidence that this also represents the flow at 100H. So just some broad statistics is this is a bit of a lower Reynolds number because it's a smaller facility. And then we ran 4 grid cases here, producing different centerline turbulence intensities. Now, the first one, the reference case around 3.7 is what you would typically see in the core of a channel flow, and these other ones are slightly elevated. Now, one of the first things you might notice is that the friction velocity has remained constant here. And that's because the pressure drop along the facility doesn't really change. So that's why in this case, the RE tau is constant with turbulence intensity, whereas in the boundary layer, RE tau increased with turbulence intensity. So all these cases are at the same RE tau this time. That is a difference between the internal and the external flows. But when we look at the mean velocity and the variance profiles, or all the Reynolds stress profiles, we see roughly similar behavior, or not roughly, exactly similar behavior, that as we increase the turbulence out here, we're getting elevated turbulence approaching the wall. With these PIV measurements, we're unable to resolve this peak, so we're not 100% sure what's happening there. But from what we can see, we have increased turbulence in the outer regions of the boundary layer, and we have a log region. And the wake follows the channel flow in this case. The green line on here for reference is DNS from the Johns Hopkins database. So our question was, what do the instantaneous structures in this flow look like, and how do they compare to the ones we saw in the turbulent boundary layer? So I'm going to quickly talk about the quiescent core, which is something else that has come out of Australia. So the quiescent core of a channel flow is this region of the channel flow, identified visually here, where you have high momentum and relatively low turbulence. Effectively, excuse me, it is a uniform momentum zone along the core of the flow. And what was found in this paper by Kwan et al. Is that it exists in channel flows for several Reynolds numbers, but you sometimes have discontinuous cores, so where it detaches. And we want to know, is this what happens when we've changed the inlet condition by adding our active grid upstream? So when we do the same analysis they did, we see that we have 3 states. We have the continuous core, which is what they found. We have discontinuous cores, which is what they found. And then we have, in some cases, no quiescent core at all. You can see that for our reference case, we don't have any of these no core states, so that agrees with the previous results. But then as we increase the free stream turbulence intensity, so that's what this is, increasing free stream turbulence intensity, we have less continuous cores, we have more discontinuous cores, and we have more cases where we have no quiescent core. So this was our broad result. Basically, we're seeing that the core still exists, but its permeance is diminished as we increase the turbulence intensity. So basically, you can imagine it like some large-scale intermittency in the facility. But Masood Asadi, the PhD student, had a good idea, which is that when you look at this, it looks like there might still be a core there. It just doesn't match the identification criteria we've used. And he performed a new form of analysis. If you're interested, check out the paper. Broadly, the way we find it is by tracking 2 peaks instead of just 1 peak, like in the original analysis. I see your hand, Min. 1 second.
Yeah, just a quick question. Is the channel tripped? Is that
there is a sandpaper roughness trip just downstream of the active grid.
Okay, thanks.
You're welcome. So what Masood found was that if we basically loosen our criteria for the detection of the core, we still find cores in these no quiescent core conditions. They just have lower momentum than the normal quiescent core. So in this new framework, he calls these ones ordinary cores, and we have our low momentum cores. Now I'm drawing lots of circles. Let's get all the circles off there. And then the next thought process was that if you have low momentum cores, then as you increase the turbulence, do you have a corresponding high momentum core that also manifests? And in fact, we can find these too. So what these high momentum cores are instances where you have a quiescent core, but inside it, there's actually an even higher speed UMZ that's flowing along. And now, if we look at the statistics of how often these cores exist, we see that indeed our ordinary cores decrease as we're increasing turbulence intensity, and our low momentum cores and our high speed momentum cores almost symmetrically increase around. So indeed, we are seeing more variation in the quiescent core, but it is still, for the most part, still there as we're increasing the turbulence intensity. So now that we're concluded on the wall-bounded flows, some main takeaways. So I've spoken for a while. Things that I want you to remember is that the inner region of wall-bounded flows is robust to what we've done to the external turbulence. That peak stays there and at roughly the same magnitude. I'm talking about the spectra in particular there. The outer regions of the wall-bounded flow are manipulated by these external disturbances. And in the case of the channel flow, this is even 100 turnovers downstream. So we can't just ignore this problem. It changed things for a long time. For instance, in an engineering application, there are many things that are over 100 lengths long, but many are shorter than that as well. Turbulence appears to rapidly mature the boundary layer, which is what we found in the earlier studies, but that this maturity isn't permanent, and it disappears further downstream. And then in terms of the instantaneous structure, it is influenced by the turbulence. In general, for UMZs in a turbulent boundary layer, they move closer to the wall and there's fewer of them. And for the channel flow, the core state is disrupted, but still present. So we're seeing more variation in the core. It's slower, it's faster, but it is still there. If you want more details, we've worked on this quite a bit, and you can find them in these papers. Feel free to email me and I can direct you at them specifically. Now, I'm going to spend less time talking about these other things, but I want to talk about some other cases where we've played with turbulence. We have active grid planar jet configuration. And what we've done here is we place our grid upstream of the jet nozzle. So we're manipulating the turbulence that's coming into the nozzle. And we want to see what this does to the jet that emits. In terms of the cases here, we're looking at 3 cases primarily. One that is just the canonical case, and we've designed this jet based on previous studies, primarily of me et al., to optimize our nozzle. And what we see is we elevate the free stream turbulence, or the turbulence at the exit of the nozzle, and then we change the integral scale substantially. So the case we're calling high has high turbulence and a very large integral scale. And the case we're calling low has high turbulence, but an order of magnitude smaller integral scale. And we want to see what effect this has on the jet. These are just smoke flow visualizations of the jet emitting. And we've colored it so it looks like PIV, but this is just, it's essentially a scalar. It's a flow viz. And what you're seeing is that the reference case has the most narrow jet, and then the 2 turbulent cases, which are these ones, have more rapid spreading qualitatively, and that the most rapid spreading is actually coming from the one with the small integral scale. If we look at the means, we see that this is corroborated. Now the lines I've superimposed horizontally here are hot wire measurements. So let's take a look at those. Close to the jet exit, we see that we're getting a roughly top hat profile. This is slightly away from the exit. But what you see is that already here, the increased turbulence cases are spreading the jet. And now, then that's this. This is the jet spreading. Now for the turbulence intensity, what you see is that we have this elevated state of the turbulence at the core of the jet, and that again, we're already seeing spreading outside of the jet axis quite quickly. If we move a bit further downstream, what we see is that we have a diminished peak and wider tails of the jet as we increase turbulence, which is what you saw in the slow viz, and that this is true also for the variance. Now, the last thing I want to talk about on this particular one is the intermittency of the barrier of the jet. So this is akin to releasing dye in a jet in water that we're using our smoke viz to see where the edge of the jet is. We record high-speed images, and we can track by thresholding it where the jet is at any moment. And what you might see is that this jet is fluctuating much more than this one. These are statistics where we're basically tracking that interface. So it's a PDF of where the interface is at each spot. So this means the dark spot means it's most likely to be there. And what you see is that the PDF is broadest when we have a low integral scale and high turbulence intensity. And the reason we think this is happening is because the integral scale is a measure of the turnover of the jet. So basically, if you have a small integral scale and high turbulence intensity, you have both high spreading and it evolves quickly because at the same physical spot, you are many more integral scales downstream. So takeaways for the jets are that increasing turbulence intensity upstream of the jet nozzle promotes rapid jet spreading. Keeping the turbulence intensity the same, but decreasing the integral scale means it'll spread even faster because it has more turnovers in the same amount of physical space. And that the boundary of the jet is more intermittent as we increase the turbulence intensity, and even more intermittent as we're increasing the integral scale, again, because it's essentially evolving faster because there's less integral scales, or sorry, more integral scales in the same physical space. And this is summarized in this work if you would like to know more. And there's also more details here where we go to 100 jet diameters downstream along the center line to see how that evolves. The last two things I'm going to talk about here are a little bit less mature, but equally interesting. So we don't have papers on these yet. So these are fresh results, and they're a bit lower order, but see what you think about them. So here we put a cylinder downstream of our big active grid in the NTNU wind tunnel. So relatively, the cylinder is big at 5 centimeters. It means that our Reynolds number is relatively high for cylinder studies. Obviously not giant, but order 30,000. And then we produce 4 different turbulent flows, all with integral scales that are between 4 and 8 times the diameter of the cylinder. So while it does change, we're still talking about something that is always order 5-ish around the cylinder dimension. It's not like it's changing by an order of magnitude. This case is the turbulence intensity measured with our PIV. When we measure it with a hot wire, it is below 1%. But I just put it there because that's what's on the figures. So let's look at some instantaneous images. So this is our lowest turbulence case. And what you see is some sort of canonical shedding shape. Now, what's interesting is if you step up to the next case, that we still have this wake, but these are all now aligned along straight behind the cylinder. And as we increase the turbulence intensity further, we're now just smearing it out. So we have more transport where we're changing the instantaneous picture in the wake of this jet. Sorry, in the wake of the cylinder. So what do statistics of this look like? Here you're seeing a step through the wake. The increasing darkness of the color is increasing turbulence intensity. And quite early on, you see this separation into 2 different types of wakes. We have the 2 lower turbulence intensities that are roughly the same, and then the 2 higher ones, which are coming onto another plot. Sorry, another peak. So now if we look at some statistics of this, we see a similar thing for the mean evolution, that the 2 lower cases fall on one line and the 2 higher turbulence intensity cases fall on another line. And that is that the deficit is recovering faster as we increase the turbulence intensity. I went too far there, but that's okay. On the right, we have the wake width, where we're seeing a slow increase in wake width as we're increasing the turbulence intensity. And that's what you're broadly seeing here. And what that's telling us is that the wake is recovering faster and it is spreading faster as we're increasing the turbulence intensity around it. And then we plotted on here the analytical results for a plain wake, and you see that it roughly falls somewhere in the middle here. But I would identify that these measurements are only up to 20 diameters downstream, so you wouldn't necessarily expect this to fit too well here, but it is surprisingly close. One thing I forgot to point out in the earlier slide is that this is actually 4 cameras and 2 lasers worth of PIV. So this is 1 meter of PIV. It's a big field of view. We look at the stresses, and we'll start off with the normal stress. This is normalized as a turbulence intensity. And broadly, what you see is that in the wake, the turbulence intensity is the same for all the cases. But in the co-flow, it's elevated as we increase the turbulence intensity. And what this means is that we get back to the background turbulence intensity faster because for the higher turbulence intensity cases, but not necessarily because we've changed the turbulence intensity in the wake, just because it has a higher state that's faster to get to. For the normal stress, we see a similar thing, except that the peak is lower for the transverse stresses for the turbulence intensity cases. And just I'm going to speed up a bit here because I don't want to keep you all too late. The shear stress is perhaps the last interesting thing, which is that it doesn't differ very much between cases. And this is about to get to the end and it'll come over again. And the reason for this is that the homogeneous turbulence has no shear stress in it. So all the shear stress is induced by the cylinder itself, and it rapidly collapses between the cases. And then it's just what's made by the cylinder. Takeaways from here are increasing the incoming turbulence intensity promotes rapid recovery of the centerline velocity. The highest turbulence intensity generated the wake width, made a broader wake width. And the normal stresses return to the level of the background more rapidly as we increase the turbulence intensity, but that is actually because it just has a lower threshold to get to that background stress, not because it changed the stresses behind the cylinder. And that the shear stress is independent of the incoming turbulence intensity, and that is because it is all made by the cylinder itself, not by the incoming turbulence intensity. The last thing I'm going to hit on here is gas transfer. So this is a bit of a step away from canonical flows, and this is something we've been doing very recently. And I think it's some interesting results. It basically says turbulence is important. So we have our water channel active grid. We deplete our water channel of oxygen using sodium sulfite. Then we let the oxygen come back into it from the lab. So the way we then do an experiment is we put an oxygen probe in to measure the bulk oxygen concentration. We do this downstream. We cover everywhere else in the water channel so that oxygen is only getting in downstream of our active grid. We do PIV to understand the fluid mechanics. We do LDA so that we get temporal response. Then the active grid also changes the surface, which means we have to use a wave probe to understand what's happening at the surface. And we do synthetic Schlieren to capture images of that surface for the different grid cases. So here's some very broad results. This is the concentration of oxygen over time. And what you can see is that as we're increasing the turbulence intensity in the water, we are reacquiring oxygen faster. So the water uptakes more oxygen if we have more turbulence in the water. Now, the question is, why is this happening? Is it because of turbulent transport? Is it because of a surface area change? Is it because of waves? So these are our synthetic Schlieren measurements for 3 cases. Just so you know, the vertical axis is an order of magnitude inflated compared to the transverse axis. And what we see as we increase the turbulence intensity, we are increasing the surface deformations substantially. But that when we look at it compared to the total new area of the surface, it is barely increasing. We're looking at a 0.2% increase in the total area. So we know that these changes to the gas concentration that we're seeing are not related to the surface area change. It has to be related to either the wave motion that we're producing or to the turbulence. And there are models that suggest both. And as we move forward, our project is to decouple these so that we can say this is turbulence, this is waves, and this is how they combine together. So the takeaways are turbulence intensity increases gas transfer across the air-water interface. The intensity increase also changes the surface deformations, and that the total change in surface area is not what is governing this problem. It is related to the waves, the turbulence, or both. And that is what the future of that project will decouple. And then just the last thing to close up, I want to say we've actually looked at the effect of turbulence on quite a few things, including cubes, vertical axis turbines, the temporal boundary layer, horizontal axis turbines, and airfoils. So I haven't included this here because it's quite broad, but if you're interested, we have been looking at this problem on many, many things. And just the last things that I want you to remember, if you remember anything, is that free stream turbulence has the effect of homogenizing the flow. So this generally promotes that the disturbed flow more rapidly resembles the turbulence that it's immersed in. So that is that the cylinder goes back to that background turbulence flow, or that the wake is smoothed off by the boundary layer. And that these effects can be long lasting. So for instance, in the channel flow, we still saw them at 100 diameter or 100 channel heights downstream, and that the effects are dependent on the turbulence. And while some global statistics just look like scaled versions of each other, the instantaneous flows are different. In general, they are more intermittent and there's more fluctuations in the uniform momentum zones and the core. So those are the main things to remember. I hope to keep developing this over time so that we can talk about some global aspects that affect everything that are more quantified. But this is where we are with this project. These are the papers I talked about today. Thank you for your time. If anyone has any questions, I'd happily take them. Thank you.
Fantastic. Thank you so much, Jason. That was a really interesting talk. We do have some time for questions. If you're in the audience and you'd like to ask a question, you can just unmute and go ahead and ask, or you can raise your hand and I can call on you in the participants list. Or if you want to just write it into the chat, that's acceptable as well. Min, did you have a question? Oh, maybe not. Okay. Oh yes. Yeah, Min, go ahead.
Well, this is more of a comment than a question. Normally, a laminar flow takes longer to be fully developed than the turbulent flow. All right? And by adding extra turbulence, all right, for example, if it was a pipe flow, the development length to get fully developed flow is shorter in turbulent flow. Therefore, you think that's a comment, right? That you actually measured, that the full flow is fully developed where you measured it. By adding more turbulence, you reach equilibrium faster. Therefore, you become fully developed faster. This is a comment.
I agree that this is a good way of framing these results. Thank you, Min. And that's why we see in the 4-meter wind tunnel that we can get Reynolds numbers that are much bigger than you normally get in 4-meter wind tunnels by increasing the turbulence intensity. But the caveat to this is that, at least in the water channel, is that turbulence density decayed. The boundary layer started to forget that it ever saw free stream turbulence. So I agree it matures it, or it brings it to equilibrium faster, but that equilibrium continuously changes as the turbulence changes, which is different than in the channel flow or the pipe where there's more turbulence sustained for longer in its core. But if anyone detects that I'm disagreeing with Min, I'm not. I think what you said is exactly right.
Great. Thanks, Min. Other questions from the audience? While people are gathering their thoughts, I had a quick question. It's not super well posed, this question, so sorry if it doesn't make sense. And you might have covered it, I might have dismissed it. But when you were talking about the turbulence kind of devolving after a while, can you comment on if the high intensity turbulence, did that devolve at kind of the same rate as the low intensity, or did it take longer or shorter?
So let's see how quickly I can effectively navigate. So in terms of just the turbulence, this plot on the right here shows how the turbulence intensity is changing over time. And if we fit a power law to it, we can roughly fit power laws of similar exponents to all the different cases. But there's only one study I know that has looked at the evolution of active grid decay in space that is published in a lot of detail. It's one by Charles Menneval. And there are a lot of similarities with canonical grid turbulence, but we also tend to get some high decay rates. And I think a lot of this is associated with the streamwise normalization. We use mesh length because that's what we've always used. But because the integral scale is changing as well, it might be a little bit unknown as to what the actual turnover time of the active grid turbulence is, because the mesh length is not the relevant one. But so to answer your question directly, yes, they all decay. And in terms of the power law, you can, that's what that black line is behind those points. You can roughly fit a similar power law to all of them. So the rate of it is similar, but there's some nuanced things about the decay of active grid turbulence that is, I would say, still being investigated by some people, including me.
Great, thank you. That answers my question very well. All right, back to the audience. Does anyone have any further questions for Jason?
Jason, I had one quick question. What's the trade-off? I understand that instantaneously you would have different effects of the active grid when you compare it with the passive grid. but statistically it will be a similar. So what is the trade-off of using an active grid, because you're putting in energy to actually move those grid elements?
Do you mean like holistically, considering even the design? Because like they cost way more.
To generate the same effect as with a passive grid. I mean, you could as well get the same effect without.
So I'd say the main
properly designed grid. That's what I said.
Yeah, the main positive benefit of the active grid is that, for instance, right here in this plot, we produce 12% turbulence intensity at 35, 40 mesh lengths downstream, where the flow is homogeneous. To get 12% turbulence intensity with a passive grid, you tend to have to be very close to it. And often what you get when you're that close to it is that you still see the wake of the bars. So your flow isn't as homogeneous. So that's where I see a major benefit of active grids, is you can produce these high turbulence intensities in a spot where the flow is homogeneous. Whereas you have to be very careful about getting turbulence intensities above 10 with no matter how you design your passive grid, because basically to get that, you tend to have to be in a spot where you still have shear, which means there's still production, which means it isn't really HIT. That's my perspective on it. The negative trade-off is that, one, these are transient flows. So like passive grid produces very nice turbulence once the wake's submerged. This, if you look at it in time, there are big fluctuations, which is what we're calling the turbulence, but it's just not, it's hard to get good intuition for it, but it's not as steady, for lack of a better word. And it costs a lot. There's also an implicit thing that people don't often think about is, if you notice on this figure, right, I said the way we get the lowest turbulence intensity is we have to spin the wings faster and faster. So what that actually means is that the lowest turbulence intensity you can produce is limited by how fast you can spin your wings.
Yep.
Which means that your mechanical limitations actually judge how small you get in turbulence intensity. And then the consequence of that is you end up with a jump. So for instance, our reference case has turbulence intensity around 1%, and then the next lowest one we can make is 5. So that's actually a big jump of situations we can't explore. So that's, I don't usually like to say the deficiencies of active grids, but I would say that is actually a major one.
All right, no worries. Thank you. Great answer. Thanks.
Great, thanks, Vishal. Any last questions from our audience? All right, otherwise, we'll thank our speaker once again for his excellent talk. Thanks. Oh, just getting a thank you in the chat as well. So thanks, Jason.
Thank you
and
so much.
I think we'll pause the recording now and see you next week, everybody in the audience.
Except for me.
Yeah.